In early 2026, a small group of physicists published a paper that did not promise warp drives, starships, or faster-than-light travel, and yet it still made people pause. The reason was simple. The math suggested that space-time might be able to bend more than our current models usually allow. That sounds subtle, but it matters. For decades, physicists have treated extreme space-time curvature as something that quickly runs into hard walls. Push it too far and the equations break, or demand impossible forms of energy. Those limits shaped how we think about black holes, the early universe, and every serious attempt at a warp drive. This new work did not break those rules outright. Instead, it questioned whether we have been stopping too early. By revisiting the underlying geometry, the authors found scenarios where space-time could be distorted more aggressively without immediately violating known physics. No shortcuts through space, no sci-fi engines. Just a reminder that our intuition about what counts as too much curvature might be off. That distinction is easy to miss. Headlines jump straight to warp drives. Physicists don't. What caught their attention was the implication that space-time is more elastic than expected, at least on paper. And if that is true, it quietly reshapes how we think about the most extreme environments in the universe. Because when space-time bends, everything else follows. In general relativity, space-time is treated like a geometric object that responds to mass and energy. Put something heavy in one place, space-time curves. Push harder, it curves more. But for most calculations, physicists assume there are practical limits to how far you can push before things stop making sense. Those limits are not always written as explicit rules. They come from experience with the equations. When curvature becomes extreme, the math often demands negative energy densities, unstable configurations, or singularities that signal a breakdown of the theory. So researchers usually stay well inside a safe zone where space-time behaves in ways we know how to handle. This mindset has shaped decades of work. Black holes are treated as special cases where curvature goes wild but stays contained behind an event horizon. The early universe is modeled with tight constraints to avoid unphysical behavior. And warp drive metrics are typically dismissed early because they seem to require impossible levels of distortion. But none of that means space-time itself is stiff. It just means our models assume it is, because going further usually causes problems. The equations of general relativity, developed by Albert Einstein, do not actually state a maximum curvature. They only describe how curvature relates to energy and momentum. What the new study highlights is a gap between physical impossibility and mathematical habit. Some regions of extreme curvature may have been written off not because the equations forbid them, but because they were difficult, unstable, or unfamiliar. That is a very different claim from saying they cannot exist at all. And that difference is where the conversation starts to change. The new study does not invent a warp drive. It goes back to the mathematics behind one, specifically the space-time geometry first written down by Miguel Alcubierre in the 1990s. That geometry showed, at least on paper, how space could contract in front of an object and expand behind it, allowing effective, faster-than-light motion without breaking relativity locally. The problem was always the same. To make the equations work, space-time had to be bent so aggressively that it required large amounts of negative energy. Worse, small changes tended to make the whole structure collapse or explode mathematically. So the metric was treated as a curiosity, not a physical proposal. What the 2026 paper did differently was stop asking how to build the drive and start asking how flexible the geometry itself could be. The authors reanalyzed the curvature limits used in earlier work and found that some assumptions were stricter than necessary. Certain distortions thought to be pathological turned out to be mathematically consistent for longer ranges than expected. This does not remove the need for exotic energy. It does not stabilize a warp bubble. And it does not allow an object to outrun light in any practical sense. What it does is show that space-time can tolerate sharper gradients before the equations fail outright. That matters because warp metrics sit near the edge of known physics. If that edge is farther out than we thought, even slightly, it changes how theorists map the boundary between possible and impossible. The result is less about motion and more about geometry. In short, the study stretches space-time on paper, not reality. But paper is where physics starts. No matter how forgiving the geometry becomes, one obstacle refuses to move: negative energy. In physics, energy is usually positive. Mass has it. Light has it. Even empty space has a tiny amount. Negative energy, by contrast, only shows up in narrow quantum effects, and only in small, fleeting amounts. You cannot bottle it. You cannot scale it up. And you definitely cannot shape it into the smooth, stable distributions a warp metric demands. The 2026 study does not change that. It explicitly avoids claiming otherwise. What it shows is that even with more flexible curvature, the stress energy required to sustain a warp-like distortion still violates known energy conditions. Those conditions are not arbitrary. They are built into how gravity behaves, how space-time responds, and how cause and effect remain consistent. Some readers miss this point and assume that bending space-time more easily somehow solves the energy problem. It does not. Think of it like discovering a bridge can flex more than expected. That helps engineers understand its structure, but it does not magically provide the materials needed to build it across an ocean. Negative energy remains the missing ingredient, and not by a small margin. The gap between what quantum physics allows and what warp metrics require is still enormous. The study does not narrow that gap in any meaningful way, but ruling something out cleanly has value. By separating geometric limits from energy limits, the paper clarifies where the real impossibility lies. The problem is not that space-time refuses to bend. It is that the universe refuses to pay the bill. And for now, it always comes due. At first glance, this kind of result can sound like academic hair-splitting. If warp drives are still impossible, why spend time figuring out exactly how impossible they are? Because physics advances by mapping boundaries. Knowing where a theory breaks is just as important as knowing where it works. When researchers assume limits that are not actually enforced by the equations, they risk missing entire classes of behavior hiding just beyond their comfort zone. This matters far beyond warp drives. Extreme space-time curvature shows up in real places, near black hole horizons, in the first fractions of a second after the Big Bang, possibly in the quantum structure of space-time itself. If space-time can tolerate sharper distortions than expected, even briefly, it affects how those environments are modeled. There is also a deeper reason. General relativity and quantum mechanics do not fully agree. Any careful re-examination of space-time geometry feeds into that tension. By identifying which constraints are mathematical habits rather than physical laws, theorists get a cleaner target for future theories of quantum gravity. The 2026 study fits into that tradition. It does not chase science fiction. It tightens the logic. It removes assumptions that were convenient but unproven. That is exactly the kind of work that quietly reshapes a field over time. Most breakthroughs do not arrive as dramatic revelations. They arrive as small corrections that make future mistakes harder to commit. This paper is one of those corrections. And in theoretical physics, those are often the ones that matter most. The renewed attention around warp drives comes from a simple shift in perspective. Once negative energy stopped being treated as a required ingredient, the idea moved from a mathematical oddity to a long-term research question. The change doesn't guarantee a breakthrough, but it shows how progress often comes from rethinking assumptions rather than adding complications. Physics evolves through this kind of steady revision. A concept that once seemed locked behind an impossible barrier now has a narrow but visible path for exploration. Curiosity is what keeps that path open. Scientists continue testing new geometries, refining simulations, and looking for better ways to understand how space-time behaves. Even if a working engine never appears, the effort pushes general relativity into new territory and teaches us more about the structure of the universe. That alone makes the work worth following.